In this video we're going to look at how you would measure enthalpy changes, and remember that enthalpy changes are delta H values from experiments. So how could we find these values, these enthalpy changes, by carrying out an experiment? And the experiment that we're going to study is something called calorimetry. So calories is a measure of energy, so it's a way of determining enthalpy change by experiment, and it involves measuring the temperature change of a given amount. So it's the temperature change of an amount of water as the reaction occurs and converting that to heat energy. And we use a very interesting fact, which is that when water is heated, it takes 4.18 joules to heat 1 gram of water by 1 Kelvin. And that's called the specific heat capacity of water. It's given the symbol C. So it's 4.18 joules to heat 1 gram per gram of water by 1 Kelvin per Kelvin. So 4.18 joules per gram per Kelvin. So we're going to use that to work out how much heat change we had. So just have a think about it. If I had 100 grams of water and heated it up 1 Kelvin, how much energy would it take? So let's have a think about that. So it's 4.18 joules per gram per Kelvin. What if I had 100 grams heated 1 Kelvin? So it's 4.18 joules per gram, and I've got 100 grams, so it'd be 100 times that, 418 joules, because I've heated 100 grams 1 Kelvin. What if I heated 100 grams 100 Kelvin? So what if I heated 100 grams 100 Kelvin? So 100 grams 1 Kelvin is 418 joules. To heat 100 grams 100 Kelvin would be 41,800 joules. So what are we doing? To calculate the heat change, and the heat change is given the symbol Q, we're taking the mass of the water, the amount of water, we're timesing it by the specific heat capacity, and we're timesing it by the number of Kelvin, the change in temperature we've heated it by. So we're not heating it to 100 Kelvin, we're heating it by 100 Kelvin. So if we start at 20 and we go to 120, that's a change of 100. So the things are explained underneath. Q is the heat energy in joules, and that is important when we come later on, that's in joules. So Q is in joules in this calculation, and the reason that Q is in joules is because C is in joules per Kelvin per gram. Now the mass of the water, the bit to highlight there is that M is the mass of the water, not necessarily the mass of the chemicals. And what we know about water is that the density is 1 gram per centimetre cubed. So if we have 1 centimetre cubed of water, we have 1 gram of water. And delta T is the temperature change in Kelvin. Now what we need to remember about this is that the Kelvin scale and the degree C scale have the same intervals. So if I was to increase by 10 degrees C, I would have also increased by 10 Kelvin. So it doesn't actually matter what I measure my delta T in out of those two, it will be the same value. So delta T is the temperature change in Kelvin. So this will be the same as change in degrees C. Now the last little thing to watch out for is that given that delta H is in kilojoules per mole and our C gives our value of Q out in joules, we're going to need to divide Q by 1,000 to turn the joules to kilojoules. Okay, so we're going to need to convert Q into kilojoules to give an answer in kilojoules per mole, And then to work it out in kilojoules per mole, we have to take the answer in joules and divide by moles. The most important thing about this method for calculating delta H is you have to decide whether it is positive or negative yourself. The calculation is not going to give you that, so you need to decide whether this reaction is positive or negative yourself. And if the temperature increases, it's negative, because if the temperature increases, it's exothermic. And if the temperature decreases, it's going to be a positive because it's an endothermic reaction. So step 1 is find your delta T and calculate Q. Step 2 is calculate moles. Step 3 is going to be turn your delta Q into delta H by dividing by Q by moles. And step 4 is put the right sign in front of it. So 4 steps to this calculation, and often is going to earn you 4 marks. So step 1. Step 1. Calculate Q. Q equals MC delta T, MCAT. Step 2. Calculate moles. Step 3. Calculate delta H, which is Q turned into kilojoules divided by moles. And step 4. Add a sign. The sign tells the chemist whether the heat energy was given out or taken in. Let's have a go at one of these together, and then we'll have a look at how we've gone on. So in an experiment to find the enthalpy change of combustion of methanol, so we're trying to find how much energy is released when we burn methanol in air. We're using 1 gram of methanol. The heat given out was used to heat 100 centimetres cubed of water, and the temperature rose by 45 degrees C. So let's just visualise that. I had a little burner, a little spirit burner with methanol in it, set fire to it, and here we're using 1 gram of methanol, and we're heating that up, and the heat is being transferred to a beaker, and in that beaker there is 100 centimetres cubed of water, and we're measuring with a thermometer the temperature, and delta T is 45 degrees C. So we're heating some water. So what we need to do is think about what's going on. We're measuring with our thermometer the amount of heat that is in the water. And so when we calculate heat energy, we'll be calculating the heat energy in the water. Then we'll be making some sort of assumption that that heat energy had to come from the methanol. And so the heat came from the methanol. If the water went up 10 joules, the methanol must have given out 10 joules. And so we can work out how much energy per mole of methanol was used. Okay, so our steps are going to be to work through how much heat energy was in the water, so how much heat energy came from the methanol, so how much energy per mole from the methanol. First thing we're going to do is have a little think about what it is we were trying to measure. So we're trying to measure the combustion of methanol. So there's methanol. Combustion is reaction with oxygen. See if you can finish that equation off and balance it. And there you go. If you've done it correctly, you should have 1.5 oxygens. If you've got 2 oxygens, remember that there is an oxygen in methanol, so you need to be careful. Right. So that is what we're trying to measure. We're trying to measure the amount of energy that the methanol here in this burner gave out. How are we doing it? Well, we're doing it by measuring how much energy went into the water. So step 1, calculate Q. Q equals MC delta T. How much energy was gained by the water? Well, how much water did we have? We had 100 centimetres cubed. Now, water has a density of 1 gram per centimetre cubed. So 100 centimetres cubed equals 100 grams. of water. So 100 grams of water, which has a specific heat capacity of 4.18, 100 grams made that water rise 45 degrees C. And remember that the difference is the same in Kelvin and in degrees C. So it took 18810 joules of energy into that water. When water goes up 45 degrees C and there's 100 grams of it, then there must have been 18,810 joules in that water. Right, now comes our little assumption. Let's just go back and look at our picture. If this water up here has increased by 18,000 joules, they didn't just come from nowhere, they've come from somewhere, and they've come from the fuel underneath. The fuel underneath must have given out at least 18,000 joules of energy. Probably gave out more, because there's probably some like going off in other directions, and some in terms of light. So there's probably more energy being released, but if the water went up by 18,810 joules, then the methanol must have gone down by that amount. The methanol must have given it out. So step 1 was calculate Q. Step 2 is calculate the moles of methanol that were used to do that. So moles is mass over MR. So pause the video, add up the MR and work out the moles. So that's what you should have got. And remember step 3 is calculate delta H. Delta H is Q turned into kilojoules divided by moles. So 18810 times 10 to the minus 3 divided by 0.03125. And I'm getting 601.92 kilojoules per mole. But don't forget step 4, delta H is what sign? So did the methanol give out energy? Was this an exothermic reaction, or did it take it in? Well, the methanol gave it out, so it's minus, and I'm also going to go for my appropriate significant figures at this point. Given all my numbers were to 2, I'm going to go for minus 602 kilojoules per mole. When you look this up in a data book, you actually find the answer is minus 715. So actually more energy was given out than we've managed to measure. Why was more energy released than we've managed to measure? And our first reason would be that we lost some heat to the surroundings. The methanol did not just heat the water, it heated the air around it, the glass beaker or the copper can, depending what you did it in. And also, when you burn methanol, you don't always get complete combustion. So if there's some incomplete combustion, then less energy would be released. Incomplete combustion is less efficient. And so that might be another reason why we get less energy.